Good morning, folks. As part of this video, our objective is to get to a fully finished liquid treatment system within a 1 hour span. So our end goal will be to get to a plant that is shown on this screen. We will start with a blank screen. This video is part of the IViewOps services series. Now, the services series part A is for wastewater or water reuse or recovery plant, and there'll be 4 videos. Not all of it may be on the site. The first is to set up a simple liquid treatment system, which we are covering now. The second is to upgrade that simple system for dynamic simulation, which we will do in a second video. The third is to add water reuse components such as tertiary treatment and certain solids handling, including energy and resource recovery. The fourth is to go to a more complex dynamic simulation with cyclic operation for aeration, which can also be used for digestion, for SBRs. The fifth is use of biofilm systems. This IViewOps is by far the most comprehensive and capable biofilm model, more accurate than any of the others in the industry because of the R&D work that was done to develop this. Part B of the series will cover water treatment and distribution systems. And part C is more advanced topics around asset management, maintenance management, investment management, and optimization. And some of these apply not just to water and wastewater, but to other industries as well. So now let's get back to this screen. This is a blank screen. And what you have over here is a module section. For the new user, what I'll do is I will dock this module section. I'll bring it over here. And I will open this up. So here you will see different modules that can be added into IViewOps. I'm using the left mouse button to move this thing around. We will start with a simple influent. The complex influent is used in actual plants where IViewOps has been set up and is running, and it can be covered in a more advanced class. We will go through the headworks, which have these, but some of these processes like equalization or holding tank can also be embedded in other parts of the plant. We'll go through secondary treatment. Here you also see chemical feed, which can be embedded in any other part of the plant. You have tertiary treatment, disinfection, filtration, etc. You have sludge handling and sludge holding systems, gravity thickener, DAF. You can also have a solid separator, which here has a dewatering icon. You can have aerobic and anaerobic digesters. And then we have a section called flow divider, combiners, and overflow weirs. Okay, let's get back to the top of this. So let's drop in. I pressed the left mouse and I dragged in and I dropped in a simple influent. If I want, I can have more than one simple influent. Like I can have the raw influent, I can have wastewater or other waste or septic that is trucked in. Now, if I want to remove this, just go to the delete button and delete it. Let's talk about what's in the simple influent. So once you drop this in, you will see in the hierarchy over here that influent comes in with 2 child assets. One is a flow controller and one is a lab. So this will have the flow data, this will have the lab data. Now, it is good practice to rename this from the default name to what it is at the plant. And one of the things I recommend that users do is, if you're setting up an actual plant as part of the services series, as part of your operations consulting service or engineering consulting or management consulting service, get as much data on the plant and its equipment and its layout before you start the work, so that you don't have to go back and forth. So I've renamed this raw influent. I can call this flow controller raw influent flow controller. I'll abbreviate it as RI. Okay, and then these are the lab data. Okay, now you can select units. You have the choice of SI and US units. For this video, we'll use the SI units. You see over here for this flow controller, if I highlight it, a default value of flow. Well, we want to run this plant at 10,000 meter cube per day. So I can enter it right here, and the flow controller is set to 10,000 meter cube per day. In video 2, we will talk about how to enter time dynamic data. But let's say the time dynamic data is in an Excel file. Let's open up that Excel file that I have set up for this plant as an example. Now, one of the things I recommend is, before you go through this series, take a break and go back through the plant series. The plant series, IViewOps Plant Series, has 6 videos. Look through that, because it'll help you a lot in understanding what we are trying to do and why we are trying to set it up a certain way, as far as what the objective of the end user may be. So please do go through the plant series, go through the intro video, and then videos 1A, which is for auto mode, 2, which is for the dashboard, 3, which is to run an alternate scenario as if you were an engineering or consulting person and you're helping the plant run alternate scenarios, and 4 is for SCADA data and other communications. Now, in the plant series, you will see that in that example, we used a 30-day average because that plant, the KNSG plant, had a long MCRT. Well, your plant may be a short MCRT plant, more like a 3 to 4 or 7 days. Then you would use a 7-day average, or it may be a medium MCRT plant. Here, what I'm saying is, this is the 15-day average of raw influent flow. It is in cell E4, and what I can do is use this Excel sheet as a source data into IVops. So how do we do that? Well, to do that, you go to this attach function under the SCADA section, click on it, and it asks or it shows which file it is attached to. Right now we are not attached to anything anywhere. So we want to attach to this file over here. You can navigate to the folder that you want. We want to attach to this file. So I click on this file, I click on open. So now you can see that the path of the file is set here. And so now if I go and say, okay, I want to link it up. Is it linked? I say yes. I go to this file, and if you have multiple files that are linked up, all the files will show up. Here it's influent 1. I'm in sheet 1, and if I look, I want cell E4. So I just say cell E4. Okay. The next step is to do an import. Well, just for your demo's sake, what I'll do is I'll change this flow to 11,000. Okay, I've changed this to 11,000. You need to save the file because IVops reads the saved version of the file. Now let me go over here, and I click on this import, and I say start. I'm doing a manual import. We cover auto import in the plant videos. And let's look at this data. You see, this has changed over to 11,000. So whatever the data is in that Excel file, if it is getting fed from, let's say, SCADA, that would show up. So I'm going to switch this back to 10,000, save this, and I'm going to go back here, and I'm going to import the new value, do a start. It says 0 errors. Once it finishes, if there are errors, you need to check what they are. and we're back to 10,000. Okay, the lab section. The lab section is of course very important, and what we are putting in here in the simple influent is kind of if you're going to set up this plant to get the correct mix liquor, in this case you would put in the equivalent of the last 15 days average of strength. In a more sophisticated plant model, there are better ways to handle that, where we use a baseline flow and an actual flow, and we look back at the last 1 year data for the baseline. But here, let's say the influent is 250. Let me look at the other file and just take a quick look here. Just to help us, I have tried and tested the file. So let's go in the input tab over here, and let's look through the lab data, what I used. 250, 230. So let me try and replicate that. 250, this one was 230 for the VSS. So TSS was 250, VSS is 230. That difference is the inner TSS. We'll get to the BOD ammonia, etc. Okay. I was entering the values in the summary section, but really what I should be doing is entering it in the main constituents, because I want all of this other information to be there. Okay, for now we will say we will use the ITSS excess of the influent. Now if you're familiar with IWA model, the IWA SM2D, you'll be familiar with these terms. Otherwise, just familiarize yourself. We'll use that. We'll say that this influent, if you characterize it in summer and winter, it may be different, but it has a volatile fatty acids of 20 milligrams per liter. How much of the influent soluble COD is fermentable? Let's say it's fraction. What fraction? 50% is fermentable. Some of it is not. Okay, let's figure out what the COD. Let's say we are going to use 450 COD. Let's say the soluble COD over here, if I look back what I used here, the soluble COD was 200. So let's say we characterize the influent and the soluble COD is 200. Okay. Now you have two other terms here, soluble non-biodegradable COD and particulate non-biodegradable COD. There are ways to get at this data by running a long MCRT plant, but let's just leave them at the default values now. These areas that are shaded, they're computed by the model. Here, let's say our actual influent ammonia was 25. Now what will happen is, since my SKN right now entered is less than the ammonia, it'll say no, you cannot do that. It'll say the value must be less than or equal to 17 because the SKN is that, so press escape to exit. So I press escape. So what we need to do is enter the TKN first, 45. Let's say the SKN is 25 and the ammonia is 22. Okay. You can have a little bit of nitrate and nitrite in the influent, that's fine, just enter that. I'm not going to go through the SKN non-biodegradable and the particulate TKN non-biodegradable. Let's say we enter the OP TSP and the OP is 4.5, and let's say the alkalinity is 250. I've skipped the soluble phosphorus, non-biodegradable, etc. Okay, you may get more sophisticated and enter certain chemical ions in the influent, certain amount of DO in the influent. You may enter certain amount of microorganisms which are there in your wastewater. Let's say this influent has 1 milligram per liter. These XaOHO is the ordinary heterotrophs, and these are measured in terms of COD as heterotrophs. And let's say it had 1 milligram of OAF, the obligate anaerobic fermenters. Let me just look what I did in the other plant that I tested and set up. Okay, and I entered a little bit of AOB and NOB. You can leave those 0, but I did enter it 0.01, let's say, or was it? Okay. That finishes my influent. I could, instead of calling it laboratory, I could call it raw influent RI lab data or something like that. Okay. So What's next? If you look here, we have put in an influence screen. So we'll do the same, then we'll go to a grit removal, and then we'll go to the primary clarifier. So how do we get the screen? Go down here. If you had a pump station, we would put in the pump station. So again, left mouse, drag it, put it here. Now, if you want, oh, sorry, this is the grit chamber, okay? This is the grit chamber. We wanted the screen. So let's put in the screen. Now what I did was I dragged this and moved this around. But you can also use this move right, move up, move down button to make small steps. Okay, I'll leave some space here because in the more advanced plant, we'll bring in the recycle from the dewatering. We'll bring in the filter backwash and all over here. So we have a screen. Now, if you look at the hierarchy, because I put the grit tank accidentally before the screen, when I was installing it, I want to move it up. So again, use the left mouse button and move it up one step at a time. So I moved it up, and here's the screen. Now the screen has a default name, but let's call it, we want to give it our own name, raw influence screen. So there it is. And then here, this is grit, we'll call it grit removal system. Okay. Now, in the screen, there is not much data to enter. Depending on the size of your screen, you'll have some TSS and therefore some particulate BOD, COD, TKN removal. The default value is 0.25%. If you have some data across the screen, based on that, figure out the percent removal. Otherwise, just leave it at the default right now. Obviously, it won't be 1 or 10%. It's a very small removal. Now, here's the grit tank. The grit tank, let's say it sends out some grit, along with it some particulate matter and some very little BOD. Let's say that's for now. We'll just change it to 0.1%. But the interesting thing about the grit tank, which is different, is it has a child asset called tank. It is actually a tank group. So I'll call it grit tank system. Okay. Now, the grit tank system comes with a default depth of 5 meters. Obviously, a grit removal system is not probably 5 meters deep, but let's say it's 2 meters deep. Okay. It could be a circular tank. It could be a rectangular. The default is rectangular. I'll show you circular when we get to clarifiers because it uses the same tank module. Now, let's say there are 2 parallel grit tanks, and so we want to install 2 tanks. You go to the cells and you add the 2 parallel cells. You don't have to have 2 icons because then your screen will become a clutter of icons. What we do here is you click on this 3 dots here beside the cell and you say, okay, I want to add another rectangular or circular cell. Well, let's say our grit system is rectangular, so we enter that. Now within each, I can call it grit tank 1. Okay. It gives a default length, which is obviously not right. Let's say this grit tank is 5 meters long and 1.5 meters wide. Okay. So I've entered that. Now you will see that there is an on-off controller, on-off checkbox and an on-off controller, and there is also an available status, which is available or unavailable for maintenance purposes. If maintenance takes it offline, obviously it's because they're working on it, it becomes unavailable. So the system has that hierarchy of bringing in maintenance information along with SCADA information. Now, so we will go through these controllers. A value of 1 means it is on. A value of 0 means it is off. Okay. So let's go to this grit tank 2 and set this up. Okay, and this is also 5 meters long and 1.5 meters wide. I think that's the value we used in the other one. Yeah. Okay. In this case, it says both are online and both are available. If for some reason we want to manually over here, or we can connect to SCADA, we want to take this offline, you can disconnect it here And then if you go here, it'll say only one is online, but both are available. If you want to shut it down for maintenance, the other thing also gets disconnected, and so it'll say in number 2, if I make it unavailable due to maintenance and I go here, it'll say only one is online and one is available. Okay, and let's say we stay with that. Now, as I mentioned, since I've gone here and made them unavailable, you'll see in this on-off controller it has become 0. Now, you could link this to an Excel file coming from SCADA, and you would just go and switch this to yes and connect up like I showed you the RON flow and flow data. Similarly, the on-off status can come from SCADA. Okay, so we've done the grit removal system. Now we get into a little bit more complicated system. We won't do an equalization right now. We'll cover it in a subsequent video, probably the dynamic simulation video, to show you an equalization. Let's put in our primary clarifier. Now, a primary clarifier is a complicated system because it also has a biological reactor section at the bottom. Now, when you start the modeling, when you're going through the first initial guess, it's easier to first set up and get to a convergence when you're still trying to get a handle on the plant by turning the biological model off. So how do you turn the biological model off? Here under the model, there's a section active or not. Well, you can make the biological model inactive. You have a whole bunch of other things here called components, processes, SGM, BGM, and PCM. They can be global or local. And we do need to understand what is in each of these. And I will get to that before I leave the primary clarifier or the bioreactor model later on. These are essentially the various components of the biochemical model and the physicochemical model over here. Let's get to this section, TSS removal. There are two methods. We'll just stay with overall TSS removal. You can have a constant TSS removal or a variable, or in IViewOps 3 with chemically enhanced primary treatment, it will compute what the TSS removal is based on chemical dosing. So you have all those features. Right now, we'll stay with constant. Variable is it'll compute it based on the flow rate for that time step, which is relevant for dynamic simulation. Let's say it has 60% TSS removal. Now let's look at this section of the primary clarifier. Let's say the primary clarifier is 4 meters deep. Okay, we're principally talking about the straight section. We could have the cone section, but we're talking about the straight section. Okay, let's leave this design maximum over flow rate alone, or if you want, you can change it to, here we're working in these units, meter cube per hour per meter squared. If I just temporarily switch it to US units, it'll give me this gallons per day. This is a pretty high maximum value. Maybe the value is more like 1,000. And then if I switch back to SI units, it gives me the SI value. Leave the specific gravity of the blanket alone. This is your initial sludge depth in the clarifier. This is the max sludge depth. These values may be a little high, on the high side, and if you want, we can lower it to more reasonable values, like, okay, the initial sludge depth is 0.25 meters, the minimum is 0.1 meter, and the maximum sludge depth in your primary is 0.5 meter, unless you're trying to keep primary sludge over there. There's a limiting underflow concentration, which is the maximum underflow concentration the sludge can achieve. Let's keep it at 100,000. There's an internal mixing section, which is the mixing between the sludge layer and the liquid layer on top. And what would happen is, as the rake arm moves, it does create some internal mixing. And if you're using it as a fermenter, you would, to release some of the soluble fatty acid products into the primary effluent, you would account for that by putting in a value for your internal mixing. This is the thickening of the solids as if it is a gravity thickener in the bottom section, and we'll leave these at the default. If the initial volume is 1,000, the volume after 1 day, think of it as a gravity thickener, is 500 out of the 1,000, and the volume after infinite time is 300, and the initial concentration is set at 30,000. Okay, we'll leave all this alone. This is part of the thickening model. Okay. The one part which I said I will get back to you is this section over here. But let's wait on it a little bit. Let's get through the setting up the other parts of the plant. Now, one of the things we'll now have to do is connect these up. So let me connect this, press this and press this, it'll connect up. It's a little different in IViewOps 3, but we'll do it here. Now, in this first video, we are not going to put in the sludge handling systems. It's as if the sludge is getting hauled out of the plant. So what I did was I went to the plant boundaries and I selected the sludge, and here's my primary sludge. Okay. Now, regarding what these things are named. Right now, this has a default name, flow stream 237. Okay, let's call it raw influent. This flow stream is raw influent. Let's call this RI screen effluent. Let's call this grit effluent. Grit effluent. Okay, let's call this primary sludge. Okay, this should ask me, this has two child assets. So let's get back here into the primary clarifier and look at what these two child assets are. There's an unflow controller, which is the flow coming out of the bottom of the primary clarifier. Obviously, it's not this high. I've set it up elsewhere, so I'll put in 50 meter cube per day. But again, I could link this to SCADA, and the SCADA could feed in this value over here. There's the tank. So what is the tank? This is actually the primary clarifier tank group. Okay, we had already set in the depth. Let's say we have two parallel primary clarifiers in this plant. And let's make a decision whether we want circular or rectangular. If we say we want rectangular primaries, we will remove the circular cell and we will put in a rectangular cell. Now, just for this example, I will use a rectangular primary, though most plants have circular primaries. So what I have to do is I have to remove the circular cell and I have to add a rectangular cell. Okay. The next thing it'll ask me is what are the dimensions of this rectangular primary? Well, I really do not know here because this is a hypothetical plant, but I'll put something here saying that, okay, it is 40 meters long and it is 10 meters wide. Okay, this one. So let's call this primary clarifier 1. Okay, I mentioned that we have two primaries, so I have to add a second one. So I go in here and I press this green plus sign. It says rectangular cell. Okay, I select that and I name this primary clarifier 2. Okay, now the dimensions of 1 were 40 and 10. The dimensions of 2 are also 40 and 10. Okay, so again, these can be turned on and off, like I mentioned, either through here or through the controllers. Now, the next little tweak over here is we want, let's say we want the flow streams in one part. Here you have the flow streams in this headworks part to be one color and the sludge to be another color. You can go in here and you have different places to select the color. Let's go here and select this to be the color of the headworks flow streams. So I am recoloring each of this and setting the color. And this is a sludge flow stream and I want to color it differently. Let's say I want to color it this dark brown color. Okay. Now we start getting into the primary effluent and how it mixes with the bioreactors. Let's take a quick look at the plant that we had set up for this class. The primary effluent comes in here. It combines with the RAS, the return activated sludge, which is coming in here. It goes into an MLE, or we could enhance it to UCT or some other configuration. Here are the tanks. We can have tanks with or without biofilm. Here for this simple example, we did tanks without a biofilm. We had one dedicated anoxic tank, one which actually can be switched on and off. The air can be switched on and off, so it can operate aerobically or anoxically at their different times of the year, or at different times of the day. And we will get to that probably in a more advanced video. And we had the aerobic zone, which we decided based on the diffuser drop legs to split up into 3. And then we had this recycle system with nitro recycle, and we had the secondary clarifier. So how do we go about building that? Now, if you think through, okay, I'm going to press the left mouse and I'm going to bring in a bioreactor here. Right now it shows as if the air is on, okay, and I'll put it in for the second anoxic cell. I need another bioreactor. Then I said, okay, I made a decision to split the aerobic zone based on the diffuser drop legs into 3. Okay, so here are the 3. Now, if I want a little bit more space, I can take this and drag it up. There you go. If I want to nudge this to the left, I can say move right, press that, or I can drag it. Now, we had a nitrate recycle come in here, and we had a combiner which brought in the RAS flow. So let's get to the bottom of this where the flow combiner is. So here's my combiner. Now as I'm putting it in here, you will see that the icons do show up right over here. So ultimately we will not need this because we kind of can follow along right from here. So here's my flow combiner for the RAS. I need a little space for the nitrate recycle flow combiner that I have to insert here. So here it is. I need a little bit more space. Now I want to show my nitro recycle coming in over the top here. So it'll come in here, and I want to flip this and use the flip horizontal, and that has been flipped. Okay. Now the next part, if I just want to continue with this and then come back to the tanks, I know that the nitro recycle system is embedded within this flow divider. And so here's the divider, and I want this part of the T to point up, so I use the flip horizontal. Okay. Now I will start naming each of these. This will become the nitro recycle. Okay, and we will put in its flow for the flow controller. I also had in this plant, I had you go to this little arrow here, go here and find the secondary clarifier. Later on, if you upgrade this plant to have a post-anoxic zone with chemical feeds such as methanol or acetic acid or micro C or something else, we will do that. So here's my secondary clarifier, and in this simpler system, we are not going to right now put in a filter or a disinfection. We can do that later in video 3, where we talk about using it for reuse. But what I will do is I will put in something over here to be able to waste the sludge. So this I will connect to this, but to connect to this, I want to flip this around, and I'll do a flip vertical, and it'll point the other way. and I have my waste sludge which will pop out of this, so I will go back up here and I'll put in another sludge. We will cover sludge handling systems in the third video. I'll connect this guy here, and I have an effluent. I will not put in filters and all. I'll just end the plant at the secondary effluent. I'll put it here. So now let's connect up all of this. This went and connected itself to this. Okay, this one was a raw influent, primary effluent and RAS PE, primary effluent, and RAS combiner. Okay, so that was this. This is the nitrate recycle combiner. Okay, you see as I'm naming it, the names get changed. Okay, so the flow from the underflow from the clarifier goes in here, the wires is split over here, and this I connected here. I'm going to connect this to this. I'm going to connect this to this. I'll keep going. And here's my nitrate recycle. And I'm going to connect this to this. Now I have the ability to move this line by grabbing the middle of it and moving it here. I can also grab it here and move it this way. So you have those, that. Now I will change the coloring of the lines in due course, but let's say we want to color the primary effluent different, give it a distinct color because it's the primary effluent. So let's say the primary effluent is colored, what do we color, what do we select? Let's say we selected this color for the primary effluent. Now if you look here on the primary effluent flow stream, it's sitting somewhere here, this flow stream. Okay, let me call this the primary effluent flow stream. So that, so I just highlighted this, press the delete button, primary effluent, that's all I have to call it. Okay, primary effluent. Now I have this flow stream 453 out of that, which was actually the WAS, and I don't want it over there, so I'll reorder the hierarchy. But how do I move this primary effluent if I want it right after the grid effluent? Well, again, press the left mouse, move it one place at a time, only one at a time, and move it up the hierarchy, and so now my primary effluent is over there. Okay, so next is this flow stream over here, which is the PE and RAS combination. Okay, so this I may want right after the primary effluent, so then I just move it one at a time up here. So I've shown you how to move these things, and I will reorder these later on by stopping the video so that we can save some time on the recording. Okay, this one is flowing into this zone. And so now let's look at the bioreactor. So this is an important part. Okay, this is the anoxic, let's say in this plant we want to call it anoxic 1. So I highlighted this, I pressed the delete button, anoxic 1. Okay, that's the anoxic 1. This is actually the system. Okay, now within the system are different assets. There's the tank group. So we'll call it anoxic 1 tank group. This is a group of parallel tanks and parallel trains. Okay, now this plant, let's say, has 3 parallel activated sludge trains. So the brute force method is to put in all the 3 trains on a whole bunch of bioreactors, but IVops has been built much more intelligently. We will have all the cells, but we will use one icon to display the 3 cells, but we can turn any one off or 2 off for if they're offline, or if they're offline for maintenance, we can do that. So here, one thing it's asked, if you look down here, let's look at the tank group for a moment. It's asking for the depth, okay, the tank group depth. Let's say the tanks are going to be 4 meters deep. And there's a whole bunch of surface area, etc. and all, but then down here it says how many parallel trains or how many cells in parallel do you have. And I mentioned this plant has 3. So there I went and added the 3 cells. Now I go to the first one and I will rename this in X1 train 1. That means it is the first anoxic cell in train 1, and I'll give it as dimensions 10 and 10. Let's say I gave it 10 meters and 10 meters. Now this has again its online and available controllers and a connected controller. We will work with that. Let's set up the anoxic 1 train 2. So this is in the next parallel train, and let's say it had the same dimensions 10 and 10. You can have different dimensions but not different depths. If you have different depths, 2 trains of different depths, you'll have to set it up as 2 parallel trains on the system. Or if you have different proportions, we do that. If you look at the real plants that have been set up, a lot of them have distinct parallel groups of tanks like east train, west train, or north or south. So, and then we have anoxic 1 train 3. Okay, and these are also 10 meters and 10 meters. Now, let's say we don't have any diffusers here in this anoxic zone. Well, you can go down below here, and it's getting hidden, so I had to move this out. And here's your type of set point. Here, well, is dissolved oxygen and airflow. Neither of these will apply, but let's go up the hierarchy before we get to the diffuse aeration system. It's going to be here, and let's look at what all choices we have. In this basin or in this cell, we can have diffuse aeration, we can have mechanical aeration, or here it is none. So I put it none and immediately change to a mixing device, okay, in the icon. Okay, so we have set up the anoxic 1 system. What I will do is I will not show you the anoxic 2, but the setup is going to be similar, and I'll get to the aerobic zone. Okay, what I've done is I've set up the anoxic 2 with 3 trains, same dimensions, 10 by 10 each. Right now I'm operating all 3 cells. What I want to show you is setting up the aerobic zone. So we'll call this aerobic 1 system. Now you may ask, well, why did you split this aeration zone from 1 to 3? Well, what happens is most plants we are finding the liquid does not mix longitudinally all the way between the front and the back. There is division if you run a more sophisticated analysis and do tracer studies. There is demarcation between the front end and the back end, and also they are using different DO set points in different parts. Whether they're baffles or not, they're doing that. And so based on how the pattern of liquid flow is in IVops, you're supposed to reflect reality. This is not just an arbitrary design. You're supposed to reflect reality and simulate what is happening in the actual plant, and then use that information to upgrade or assess the plant. So, and to optimize the plant. So what we are doing is we have, in this case, what we find in most instances is in the BNR and ENR plants, the aerobic zone has longitudinal demarcation. So here's the aerobic 1 system, and we need to either here or elsewhere, the depth is going to be 4 meters. We are going to work through the diffuse aeration system here. Okay, so we will go through and set up the tank group. And we mentioned that this has 3 parallel trains, so we go here into the cells and we add the two others. We will name this aerobic 1 train 1. Let's say this is also 10 meters by 10 meters. We'll keep all of them on. We'll call this aerobic 1 train 2. And this is also 10 meters by 10 meters. And we will call this aerobic 1 train 3. And this is also 10 by 10. Okay, so these are 3 parallel trains. Right now we're keeping all 3 online. Later on we will shut one off. Okay, next part which we have not covered in the anoxic is, okay, what is the alpha and beta, etc. Let's say the first aerobic zone has an alpha of 0.55. Okay, this comes through calibration with the plant or against the plant, etc. Let's say we have membrane fine bubble diffusers, and its efficiency is 24% at 12 feet or 3.65 meter depth. We will cover how to assign which blower is or blower group is servicing which part of the plant in a more advanced video. So we are in the diffused aeration system. If you open up the hierarchy of the diffused aeration system, you will find there are 2 important things. There's the DO set point, and then whether the air is on or off. You can cycle the air on or off. Now, I can enter the DO set point, let's say it's 2.5 right here. Or if I want to connect it to an external file, like an Excel file fed from SCADA, I say, okay, let me bring it in from that file that I was working with. And it's I have the data only in this sheet over here. Let's look at that file. Okay, let me go not here, but here. And the average DO is 2.65, and it's in cell J4. So I go in here and say this is cell J4, and I've just set up the link. If I want to test the link, I press import. I import the data, and you will see this value went up from 2.5 to 2.65. If I want to bring in a stream of data where the DO is different at different times of the day, I can again look here. I had different DOs at different times of the day, different flow rates, different wasting rates, and we will cover this in video number 2. Different DO levels, and when we go to air on and off, the air is on and off in an anoxic zone at different times. So we have all this. So the DO level can change at different times of the day. We will cover that when we bring in the dynamic simulation data. Okay, the on-off controller here. Well, what we have done is essentially we have said there is a diffuser here, and if the air is on all the time, this value will be on. If the air is on or off at different times of the day, we'll bring that in through a time series, and we can connect this up over here. So the diffused aeration system has 2 child assets. One is the set point controller, and one is the on-off controller. Now, you could have this plant operate on airflow rate over here, and I won't cover this here, but yes, you can change it to, instead of a DO set point, the airflow rate can be your set point, and the airflow rate can vary at different times of the day. So I'll leave this in dissolved oxygen. Now what I'll do is, again, I will stop the recording, and I will set up aerobic 2 and aerobic 3, and I'll come back to this. Now one thing I want to show you is that in aerobic 2, under its diffused aeration system, the alpha may not be the same as aerobic 1. In fact, the alpha may have gone up. So what I've done is I've taken the alpha up from 0.55 to 0.6. There's the same type of diffusers here. And regarding the set point, I could have a different cell and a different data stream that of DO that is feeding in here. But for this simple file, I'll use the same cell as I used for the first aerobic zone, the aerobic 1 system. So I'll use the same J4 over here to feed it. But in a real plant, it wouldn't be J4. It would be something like column K4 or L4, some other data stream. Okay, so I will link that up later. Now I will move on to setting up aerobic 3, and now in aerobic 3, what I've done is I have again increased the alpha from 0.6 to 0.65 for this plant. Now in a real plant, you would calibrate the airflow to the actual airflow for an actual condition, and that way you can get to the values of alpha that you experience at a plant. So I've set up aerobic 3. One thing we will come back to later on, I had mentioned, was these models, and we will come back to we will have to come back to dampening flow. So this is a good place to look at what the components are, processes are, SGM, BGM, and PCM. The place to go here is go under model, look at components, and you can set what is running and what is not running globally across the entire plant, or you can set it up locally, and I'll show you how to set it up locally to be different for a particular bioreactor in a particular tank. You have these components. If you're familiar with ASM2D, you will know all of these. We are not feeding methanol, so the methanol is turned off here. All the other components, including production of acetate, etc., are turned on. Since we are not feeding chemicals like iron and aluminum, or we do not have a digester, we are not simulating some of these parts, but we could, if we wanted to, we could turn it on. But my advice is, if you're going to feed ferric, turn on the ferric model. If you're going to feed aluminum, turn on the aluminum model. Now, particulates. These are the bacterial species. We have turned on the OHO. We want to have some fermentation in the primary, so we'll turn on the OAF. Methanogens, when we put in the anaerobic digester, we'll turn it on. Right now, there is no need. PAO, we'll leave it on. Methanotrophs. The methanotrophs, since we're not feeding in methanol, we will keep them off. Ammonia oxidizers and nitrite oxidizers, we have them on. Anammox, we don't want to do it right now, we'll have them off. Okay, again, follow a philosophy of not overloading your model and running things which exist only in your imagination and have very little real bearing. We are not trying to do R&D project which is completely different from how the real plant operates. So, unless you're confident that you're really operating for Anammox and it is going to be a significant species, not a very minuscule population of Anammox, but you are going to breed a significant population of Anammox, then turn it on. Otherwise, do not. It just creates a nonsensical result which is devoid of reality. Again, that comes from experience working with over 500 plants, but then I just want to convey that if you're going to fire a rocket to go to the moon, do not design it to go to Jupiter. That's what I'm trying to get at. So let's continue through processes. Okay, as far as the processes, we want to run the OHO, we want to run the OAF, we do not want to run the methanogens, we want to run the PAO. There's no methanol getting added, so the methanotrophs are not necessary, and we will shut off these because we don't need the Anammox and all on this. As far as parameters for the SGM, now this will take some time. It is a much more advanced topic, but I just want to give you a flavor of it and give you a few quick tricks. If you're running a plant in the US, we find that the decay rates are still lower, even though we have reduced it below the ASM2D. The true decay rates are a little lower, especially plants which are operating tend to optimize for energy and do not over aerate with a high DO set point. So the OHO decay rate on aerobic is around 0.12 because not 100% of the inside of the flock is aerobic. Maybe the anoxic decay rate is more like 0.08 instead of 0.1. Those of you who are not familiar with Arrhenius coefficient, just familiarize yourself. But here's the Arrhenius coefficient, which tells you how the decay rate changes with temperature, and you can set that. And let's say the aerobic, the anaerobic decay rate for OHO, will set it at 0.04. Okay. I will not go into OAF right now for sake of time, but let's quickly take a look at AOB. Under AOB, what we find in real plants is, unless they're high rate plants, the half saturation constant for DO in the longer MCRD plants is more like 0.5 in the real plants. The half saturation constant for K ammonia at 20 degrees Celsius is also like 0.5. You can feed in an Arrhenius for changing K ammonia with temperature. It can be greater or less than 1. For NOB, similarly, the KDO may be a little less, a little greater than 0.5, maybe more like 0.55. Okay. Now, there are things under hydrolysis that you'll become familiar with. Things under stoichiometry you'll become familiar with over time. But let's go to conversion factors. One of the conversion factors here is what is the biodegradable COD to BOD ratio of the particulates, and most plants it's more like 1.75. So I'll change it here, and what this will do is change the influent BOD for the amount of COD here, and I'll save this. I also have the ability, if I want, to go in here, go to this, and save the model as a little SGM file. So if I press this, it says, well, do I want to save this? And I'll override this file. I had already saved this here. I'll just override it with this new data, and I've saved that file. And I can import that file back into this or another plant. So I can save the coefficients of one plant and import it into another plant or another file. Okay. Now, few other things over here. BGM is the biofuel model. PCM is the physical chemical model. Again, there isn't enough time on this video to cover those things. And then there are some constants over here, which is the partial pressure of CO2, which you can change locally for the for an anaerobic digester. The other one, if your plant is at sea level, you can leave it at that default thing. If your plant is at 8,000 feet high, obviously a partial pressure of CO2 is going to be different from the default. Okay, now one other thing. I live in California. We design buildings with dampening for earthquakes. Well, similarly, in the liquid treatment, dampening function does help you with your convergence. Initially, we had the model discover what the dampening rate is going to be, but for now, we have made it a little simpler. And you can enter a dampening flow, which you can think of as the internal mixing flow with the mixer running here. So it's only taking place within this bioreactor. It's not going around. It's just the internal mixing. Now, that can be quite high, but right now we'll just enter it to be equal to the influent flow rate of 10,000. So for each bioreactor, it's not necessary to have a dampening flow for everyone, but I will, at this stage, just introduce you to this and say, okay, I'll set each up to be 10,000, which is the influent flow. Now, for solids handling systems and all, like digesters, the dampening flow in an anaerobic digester may be 20 times the sludge flow going into it to help it with its convergence. It does not affect your effluent results. It just is to prevent a big oscillation and a longer convergence time when we run the model. Now, when we get to the secondary clarifier, we'll also have to deal with how we run the secondary clarifier. Now, the secondary clarifier in more complex IVops 3 has within it a stilling well volume, a clear liquid volume, and sludge volume, which is computed based on steady state and dynamic simulation. Here, in this release of IVops 2, we have to put in the stilling well separately and the clear liquid volume separately if you want to simulate those as separate bioreactors, but the sludge is included. So let's look through what is in the secondary clarifier. Here the model section will keep it active. Unlike the primary clarifier where I think I shut it off, in the secondary is fine. Let's start with it on. Okay, TSS removal. Well, what happens is you can have a more sophisticated model of the thing, but right now, let's say when we run it, there's 99.7% TSS removal to get it started with. Let's say the depth is 4 meters. Now, we will get to dampening flow rate a little later. We'll get to this maximum overflow rate, etc., and this sludge volume and which equation to use for settling. Before we go there, let's look at what is this underflow controller. Well, this underflow controller is the underflow from the secondary clarifier. So let's call this secondary clarifier underflow controller. It'll become RAS after we split out the WAS. If you want to call it RAS, that's fine. Okay, let's say this sludge flow here is, we could link it up to an external file, but let's say it's half the flow rate to the plant 5,000 meter cube per day. So here I've entered it directly over here. Okay, now you have the tank group. So this is the secondary clarifier tanks. We had already given it the depth, but let's say we have 2 circular secondary clarifiers. Okay, so now we have to enter the dimensions, and let's say they're each 30 meters. Maybe 30 meters is too large for this plant, but they're each 30 meters. And I'll call this secondary clarifier 1. And I'll call this secondary clarifier 2. Okay, I've kept both of them online. Now there's another section called lab section, and if I open up this is where it asks for the SVI. And as a practice, we bring in the last 7-day average of SVI if you're running it inside a plant. But let's say the SVI in this plant is 110. Okay, I brought it in here. You can connect it to the lab file. Okay, so next thing over here is this flow divider here, which is actually the WAS splitter. Now you can have pumps or you can have a valve. And the WAS splitter has the WAS flow controller as a child asset within it. So I'll just go here, WAS flow controller. Let's say I want to link it up to the Excel file, so I'll just do the link. Let's find where the WAS is. The WAS is over here in cell G4. So I'll say G4. If I want to, right now the value is 0. Let's do an import. Okay, something happened here. I don't know what I imported, but I'll have to look up why it did not update it. Okay, it's updated here. Okay, now it's updated. Okay, there you go. The WAS is updated. I was on a wrong asset. So I have the WAS here, 115.1 is the WAS flow. In the Excel file you see 115, but the decimal place is hidden. Okay. So now getting back to the clarifier, you could, just to be safe, enter a dampening flow equal to the RAS flow. You may not need the dampening flow. Let's see. For dynamic simulation, these are important. Well, there's an initial sludge level which is used in steady state, but in dynamic the sludge level varies based on flow rates to the clarifier. But we do set a minimum sludge level and a maximum sludge level. What happens is if the sludge level hits the maximum, after that the excess solids start going out. If it's going to build up more, it starts going out in the effluent. So we have that here, and there are three equations here for sludge settling, but we'll stay with the middle one, the middle of the road one. Okay, so one thing we did not cover as yet is this nitrate recycle. So this nitrate recycle, let's say we are operating at 4 times the influent flow. So let's set up the nitrate recycle flow controller. Okay, and let's say we are operating at 40,000, 4 times the influent flow, 40,000 meter cube per day. Now I could link it to an Excel file, but right now I have not. Now, one place, okay, you can scroll back here, use the scroll button and scroll back here, is that IViewOps also brings in the equipment. Now, what I'll do is in the I'm looking at the time. In the second video, we will go through and bring in the equipment. But what I am trying to do next is I should go through a file save. I should do a save as. I've not even saved this file, which would be a mistake. I did not save this file all this time. Let's call it IViewOps Services 1. I've got it 1-1 because I had a file 1 open. Okay. Now, the next step is to try and get ready to run it. And you may face some initial challenges because you made some mistakes here. But it is good practice to go check all your volumes and make sure your volumes are coming out the same volume of 3. So I'm pressing on each of this. I'm checking the volume. And there may be a few errors here and there. If I forgot, now this one, it seems, has a weird effective volume, and right now I do not know why, but I will get back to it. Now, one of the decisions I need to make is, should I operate with all 3 trains online, or should I shut down one train in the system? Now, I wanted to demo how you would shut down one train. So I mentioned that this thing could be linked to Excel, and Excel is bringing a value here whether the train is online or offline. But what I'm going to do is I'm going to manually shut train 3 down in the activated sludge system. So I'm going to go into each of these. I'm going to open up the tank group, and I'm going to go to train 3, and I'm going to shut it down. Okay. So and I'm going to simulate it with only 2 trains in activated sludge, but both the clarifier is online. That's what I'm going to do. So now let me quickly take a look that I've done it on all. So if I look at aerobic tank, aerobic 3, that has only 2 online out of 3. Aerobic 2 tank group, that has 2 online out of 3. Aerobic 1 tank group, that has 2 online out of 3. Anoxic tank group, 2 online out of anoxic 2, and then anoxic 1, 2 online out of 3. Okay. Let me save this. Now, how do we get around to running the model? Well, right now I'm allowing a maximum number of iterations of 10,000. Maybe I need to increase it to 20,000. In more sophisticated analysis, I increase the evaluation frequency from 99 to like 299 or 499. Sometimes I even go even higher, but I think you should not go any more than 299. Because if you get stuck in dynamic simulation, it needs to run through the full 299 steps before it makes a tweak and then runs it to help it converge. The maximum absolute error for large plants, I use 10,000, which is a small error, but I'll leave it at 1000. This is at 1E7. I'll change it a little, 001. Okay. Now, steady state. These are the initial guesses where it'll start, and once I converge from the initial guess, I will get to the next part of the plant. We will not cover dynamic, and we will not cover optimization here. So let's try to see what happens if I press the run button. I press the run button and I press start, and it starts working through and trying to converge to a solution. Now it may get stuck, and it may have to run through a lot of iterations. It may wiggle a little, but if you have put in your dampening flows and if you have not put in extraneous parameters that you're running, it should be fairly simple. Let's look at the mix slicker that we ran, and when I click on a flow line, I get the mix slicker. Let's undock this guy. We don't need it anymore. I'm going to undock it, and I'm going to shrink this panel. Okay, so I have this flow stream here, which I should have named, but I have not as yet. But this is secondary clarifier influent. So it is still mix slicker, but it is secondary clarifier influent. Its mix slicker is 2660. VS is 2440, the ammonia is 0.15, and I'll show you the temperature it is running. But if you want more details, you go into the main constituents and you'll see all these details. If you want to know how much of what microorganisms you have so much OHO as COD, so much PAO, so much AOB and NOB in the system right now. Okay, few things. I have not named all these flows, but I should have named them, and it's good practice to do so. So I will name a few, but then I'll stop the recording and do the other ones offline. Now, the other thing over here which we have not talked about is what data do you want to save. Depending on what data you want to save, the file will become larger in dynamic simulation. If you want to save the secondary effluent data for dynamic simulation, you check this. If you're running an optimizer in steady state or in dynamic, you can check this. Now, secondary effluent, we may want to color it differently so that we can easily find it. And let's say we color the secondary effluent to be this blue color. So now if you look here, the secondary effluent has a different blue color. Now it's sitting in the middle of other flow streams, and I will have to move this around, which I will do. But now let's go to the next step of getting it off the initial guess, so that we're not rerunning from an initial guess, but we're running from the previous guess. So I've unchecked this button, and then I have to, when I rerun, if I do not disturb it a little bit with a slightly different DO or a mix slicker, what happens is the model will say, oh, it is converged, even though I rerun it because the disturbance was very little. So we enter a little bit of a perturbation factor, which is here, and a value of 1.01 for a small plant like this, or 1.001 is good. So let me rerun this, and it'll now start from the previous guess values, and you can see that it converged pretty quickly. So what I have not done is I have not turned on the primary clarifier. Now that can create a bit of a problem, and I might have to go back to starting from an initial guess, and it's good practice to first save this file. So you've saved it, maybe save it under a different name, and then you go back here and you turn on your primary. Now, one difficulty you'll have with the primary is you don't have the recycle from dewatering and the recycle from filters coming into the headworks, which adds a little bit of biomass here, which helps the primary clarifier. So I don't have the advantage of all of that. I have also not probably put in a dampening flow, but let's say I put in a dampening flow equal to the primary sludge flow over here. Now, because I don't have the sludge recycles baked in, I might have to start from an initial guess. And if I start from an initial guess, it may oscillate a little bit more, but I'll give it a shot. So I will restart from an initial guess here, even though I have to, but I will do it. and I'm going to rerun this and see what happens. So the primary clarifier sometimes, unless you have the recycles from dewatering now built in, takes a longer time to converge or may have some difficulty in converging. But let it run through. It seems, oh, I have too many things open. Okay, so this is what I did because it was getting stuck at a certain value. I increased the residual error, and I also increased the dampening flow, and that allowed the initial guess to converge. So what I did over here is I increased the dampening flow right now to 200, and what I went in here is I went into under general, and I increased this maximum allowable error to 30,000. I can bring it back to 10,000, and when I get off the initial guess, now it should be easier for it to run. Let's see what it does. There you go. So the initial guess, because it's starting from, especially the primary clarifier, is starting from mixed flickers, which are quite different from what it is over here. I should have used a local initial guess, which is more like what bacteria populations are here. But because I didn't, I had to kind of increase the residual error and then get it back down. Now, if I want, I can bring this dampening flow back to about the same as the sludge flow, and I rerun it. And there you go. If I want to change the residual error, because this is a small plant, from 10,000 back to 1,000, I've done it, and rerun it. And here you go. So if I look at the primary effluent, it has certain characteristics, certain flow, TSS and all, which are different from here. Now, one of the things I did not do in this primary clarifier is allow a mixing of the sludge layer and the upper layer. But if I want to do that, I need to put in an internal mixing rate of, let's say, 100, something like the sludge flow rate, or something a little higher, 100 meter cube per day. And if I rerun it, there'll be some of the sludge layer that will get mixed into the rest of the liquid, and you'll see some of the ammonia from the sludge move into the liquid, some of the acetate move into the liquid area. You can do the same for the secondary clarifier. There is a little bit of mixing between what is happening in the sludge layer and the upper clear liquid layer. Now here again, I might have the residual error set too aggressive, so I might have to change that so that it finishes the convergence. Or I might have to just let it run for a little. So what I did was I increased the residual error to 2500. Now I have this internal mixing. You can see that VFA coming in is 20, and VFA in the primary effluent, I should have pointed out, is 22. So there is some VFA being released. Again, back here, if you look at the VFA is 20 going in the grid effluent going into the primary, and VFA leaving the primary clarifier is 22. So there's some VFA released. If you look at the primary sludge, its alkalinity is lower, ammonia is higher, the VFA is 235. The primary sludge has a lot of VFA. Now, I will not show you, because I've done it elsewhere, how to recolor these streams, but it is good practice to go select a color for each of the flow streams and rename it. For example, this flow stream coming out of aerobic 3, I should call it aerobic 3 effluent. If I want to save its data for dynamic simulation, I should go here. If I want to customize the color, let's say I want to select a mixed licorice color, I change that here. Now, if I want to move this up and show it up here, I will click on this and then press the left mouse, move it one at a time up. Don't move it several steps at a time. You just have to be patient, but you have to do it only once. I moved the aerobic 3 effluent ahead of the secondary effluent. So I would go rename each of these flow streams. I would also study values like, okay, what is the TSS here, what is the ammonia here, etc. What is the orthophosphorus in this stream as compared to the secondary effluent. Secondary effluent has OP of 2.26 and an ammonia of 0.14. The sludge, the underflow, has ammonia of 1.97. No nitrates, is denitrifying, and a higher OP. There's some biological excess phosphorus removal and phosphorus release. So let me save this file. And you essentially have your first plant set up. Now, in the next video, what we will do is we will put in the time dynamic nature of the influent flow. We will change the DO at different times of the day. We will also change the wasting at different times of the day. In a more advanced thing, we'll put in a flow equalization over here, and we will show you that. Then in the third video, we will add in the filter. We will add in the solids handling processes and the recycle from solids handling. And then in the fourth video, we'll get to more advanced dynamic simulation. Some of these videos will not be will be available only to people who go through classes, but others will be available on the website.